unit. Yay. Okay. All right. Polynomial functions. We are going to start to stretch ourselves a little bit. Now, instead of just quadratics or linear things, we're going to get into exponent of 3, 4, 5, and things like that. So here's how this is going to work. When we're looking at degrees of things, in Algebra 2, when we look to graph and kind of solve with stuff, most of the ones that we work with are in this area. We've graphed cubics. We just got done graphing quadratics. We graph linear things that make lines. We don't talk a lot about the ones beyond that, though, because we don't look at their graphs as much. But it's still important to understand what the names are of those things. And they're all based off of the largest exponent that you see. If the largest exponent you see in an equation has an exponent of 1, it's linear. If it's 2, it's quadratic. If it's 3, it's cubic. But we're always looking at the largest one to determine what type of polynomial that it's going to be. So as we get down here into this box, scooch this up a little bit, we've got to decide whether something's a polynomial or not, which we'll discuss. And then if it is, we're going to write the function in standard form and go about our business. So, when we get down here, standard form means we're going to go from the largest exponent to the least. The least being if I have what's called a constant term, which means there's no variable on it at all. So, which one of my terms in number 1 has the largest exponent, the largest degree? Okay, and good. We have to take whatever coefficients with it along. So if it's negative, it has to come along negative. What's my next term going to be? Okay, so plus, because it's positive, 1/2 x squared minus 7. Greatest degree to least, largest exponent to least. So we'll be talking about those according to degree. Speaking of degree. Largest exponent we see on a single term. Sometimes it'll get to be where you may have multiple variables in a term. You'll have to add those, but that's the only time that'll happen. Otherwise, it's just the biggest one that we see. Okay. What's our type going to be? Quartic, okay? Because the type of polynomial we have is based on its degree. If it has a degree of 4, it's called a quartic function. And then what's our least coefficient going to be? What number's in the very front of my standard form? -3. You want to be careful when you're asked for a lead coefficient to be sure that you put it into standard form first. Because if you just left it the way it is originally, you'd say it's 1/2. But that's definitely not the case for what we're doing on this one. What about the next one? Yeah, it's already in standard form. What's my degree? 3. So it's cubic. Okay. And my lead coefficient is 2. Bump up a little more here. What about number 3? Okay, 2x to the 5th is first, as the largest degree. X squared plus x. Now run the rest off. 5th degree. 2. Now here's one other thing that may happen to you sometime, even though we haven't seen it yet. You may get a function that has 2 terms with the same degree. You may have to combine like terms before you can actually start putting it into standard form. Just something to be aware of and to think about. Ooh, this one's weird. All right, what about this last one? Ix squared minus 5x minus the square root of 2. What are the rest of the things that we have? The coefficient pi. What type is it? Quadratic. Now, you'll notice up above, oh yeah, yeah. Because pi is just like any other coefficient. It would be like having to be at like 3.14, whatever, x squared. Yeah, absolutely still graph that. Determine whether it's a polynomial function. All of these were, you're like, well, what would be an example of something that wouldn't be then? Something that wouldn't be, okay, if I have an x term in the denominator of a fraction, which we didn't see here. So if I had 4 over x in something, it wouldn't be a polynomial function. And I'll explain in just a second, because these two I'm going to write down go together. Or 2, if I have a negative exponent. And you're like, well, why is that? If I went to graph it, it wouldn't pass our vertical line test. Okay? It would cross in more than one place. So x in the denominator, if you think about it, really is a negative exponent. Because if you had 1 over x, what is that really? It's x to the negative first. So if you ever see either of these things and it asks you, is it a polynomial function, you can just say no, and you don't even have to worry about the rest of this. But these are all examples of what a polynomial function would be. So if it's either of these, then it's not a polynomial. Well, not a polynomial function, let me put it that way. Oops, I'm going off the screen. It's a jumbo sized here so we can see. So not a polynomial function if we see a negative exponent or if we see x down in the denominator. So once you get a feel for what standard form is, and how to find a degree, because the degree will directly lead when we start graphing this and tell us how many solutions there are. If something has a degree of 5, there's going to be 5 answers. If 3, there's 3 answers. If it's 2, we just got done with quadratics, you're typically getting 2 answers. So once we kind of start to use that now, one way I can evaluate it is direct substitution. This is the one we like the easiest. For example, if I had this and punched it in a calculator, but I only wanted to know what the value was of 3, one thing I can do is everywhere I see x, I basically just plug a 3 in. Now, one thing I want you to be aware of, this f of 3 is not part of what I'm trying to simplify. That's just there as a label. That's like saying y equals. Okay? It's just letting me know I want to know the value of the function at 3. In other words, if x equals 3, what does this equal? Is what I'm going to do. So whether I punch this part into the calculator or just do some mental math with each of the pieces, I'm just going to kind of work my way out here. So 3 to the 4th is 81, 2 is 162. Some of you are like, I'm going to get down the calculator faster. We'll see. 105, maybe 8. So all we're doing, and again, this would be my f of 3. It doesn't mean now I divide by 3 and say f is some decimal number, like 32.6. Not doing that. That's just a label. Okay? So as long as we keep that off to the side, it should be fine. And again, when we evaluate, it's just basically saying we're substituting. Take that negative 4 for x, literally just plug it in. So it's just 3 times negative 4 minus 5. It's just basic old school substitution. But you still got to be careful. Because some of you get nabbed on little things with signs all the time. And this would be f of negative 4. Okay. F of x, again, just a fancy way of saying y. But now that we're moving more into upper level type things, this is the way we talk. Sort of like going from baby talking to talking like a normal person. Same idea. Now when we start throwing fun things in like absolute value, what's something we know about absolute value? Okay, it's going to whatever comes out of those bars is going to come out positive. If it's an inequality, we might be able to get into some things that two answers are solving, but here we're only going to be getting one. But I'm glad you're thinking about this. Because here, when I substitute in, 1 minus 2, very true, is negative 1. But when it comes out of the absolute value, because the absolute value is distance, we never talk about distance in a negative way. It would be the equivalent of driving somewhere and your odometer is going backwards. It doesn't happen. So this is really 3 times 1, which is 3. So f of 1, okay, just saying I'm plugging in 1 for x, equals 3. Okay, and I want you to get used to looking at the labels. When you get to standardized testing, this is what it's going to look like. So I want you to be familiar with it, even though I'd understand if you just said y equals 3. Okay? The only other thing you want to be careful of, and that's why I mentioned the statement we have just below it, whenever you go to substitute, you need to use parentheses. So for instance here, when I plug in that negative 2, that needs to be in parentheses. Because then I don't lose the value of the negative. Because there's a difference between negative 2 and parentheses, that quantity squared, and if there wasn't parentheses there at all. Negative 2 quantity squared is 4, positive. Times 4 is 16. 2 times negative 2 is negative 4 minus 1. 16 minus 4 is 12, minus 1 more is 11. And like it mentions down below, some students do find it easier to use the store function on the calculator to not have to worry about parentheses. Now, if you're interested in doing that, let me show you how this kind of works, just so you can see what's happening here. And actually, instead of doing it on there, I'm going to do it on my regular one this time. So I don't want to mess with our video here. So let's say I wanted to do, I'm just going to do the easiest one here, number 6, and I'm going to use the graphing calculator to do it. Basically, what I would do here is I got to tell the calculator first what I want to put in for here. So here's how this works. I'd have my, oops, clear that out. I'm going to have the store button. And I think I just hit my button backwards. I did. Silly man. So if I want negative 4 to be this, type in the number you want x to be, and hit the store button. It's right above the on button on the left side. This little arrow comes up. If you put the x in there, and then hit enter, you're like, okay, well that just says negative 4. That's not the answer. No, but the calculator now knows anytime that I type in the next expression, wherever it sees x, it's going to plug in negative 4. So if I type the expression in that I want now, 3x minus 5, and hit enter, negative 17. It does the work for me. That's nice sometimes on these, especially if you have a longer problem and you tend to get a little careless with some of that stuff. It's a good double check, but it takes some time. So this isn't something I do for every problem because, especially if you get to a test, some of you are going to run into a time issue. But it's a nice backup tool if you're not sure sometimes. So if we flip on over here, we're going to start talking about what happens when we see the actual graphs of some of these. We're going to talk about what's called end behavior. Basically, we're going to look to see what happens if it's going off forever in whatever direction the graph happens to go. So when we do this, we're going to see funky notation looking like this. And it's always going to be written, f of x approaches negative or positive infinity as x approaches. Now let me explain what this is going to be like so you can see how this works. I like to draw pictures on these. Now, again, if you have the calculator, you don't have to worry about it as much. But for instance, discuss the end behavior for f of x equals 4x. Okay, if I were to make just a quick sketch of this graph, I have a pretty good idea what it's going to look like anyway. So So if I went to y equals, figure out anything that's there, and I just typed in 4x, graph. I know it's going to be a straight line. It's linear, okay? Now, it's not important that I'm perfect with this, but when I look at it, here's what I'm looking at. Remember, f of x, let's bring it back down here a little so we can see this, is a fancy way of saying y. So my y is up and down. So when I'm looking at my y values, my f of x, and I'm going to copy this exactly, actually, so we can see how this works. Okay, here's basically what we're being asked. As x approaches negative infinity, okay, which is going to be as I'm coming this way. So here's my negative infinity for x. If this line keeps coming this way, are my y values getting greater or smaller? Smaller. So are they approaching positive infinity or negative infinity? Negative infinity. So basically, once you have a picture of the graph, what you're going to ask yourself is, in regards to x, so in other words, as I keep going to the left with my graph, what's happening to my y values? If they're going down, I use negative infinity. If they happen to be going up, I use positive infinity. And then I look at the other side. I say, okay, positive infinity for x is going off to the right. So if I follow the line and keep going as it goes to the right, am I heading towards positive or negative infinity? Positive, because I'm going up. So how this would read is, f of x approaches negative infinity as x approaches negative infinity. Because as my line goes left, it's also going down. Then this says, f of x approaches positive infinity as x approaches positive infinity. In other words, as my graph goes to the right, it's also going up. So the only things you have to make a decision on each time is this place that we've drawn things in red. Everything else is going to be the same every time. It's still going to start with f of x for both. You're still going to have one that says as x approaches negative infinity, and one that says as it approaches positive. Your job's going to be to figure out what goes in the blank. And to do that, again, I just need quick sketches of things. So for instance here, boost this over a little, if I type in negative 4x squared. Now again, x squared we know is a parabola. What else do we know since it's negative 4? It's flipped. It's opening down. So even if I just had a general idea, it doesn't have to be exact. Even if I just sat on this one and I'd have been like, okay, something like this. As long as I have an idea, a sketch of the picture, it should be easy for me to figure out what goes in the blanks. Because again, I start to look and I say, okay, as I'm going to the left, what's happening to my graph? Which direction is it going? Down towards negative infinity. So then I say, okay, well now I'm going to the right here. Which direction am I going? Down. So it's also negative infinity. Sometimes on these you can have one of each, like we did in number 7. Sometimes they can both be going down, like they are in number 8. I wonder if we can get them going in the other directions here. So again, you're just looking to see if your graph heads down as it goes that direction for x, we use negative infinity. If it heads up, we use positive. But again, the general part we're doing here is always going to set up the same. Now this is a graph we haven't had much experience with. So let's see what this guy looks like. And again, if I had to, if I didn't have access to a calculator, I could just plug some values in to get a general idea of what this looks like. Negative x to the third plus 5x minus 1. Graph this. That's kind of funky. So it goes like this, like this. And again, I'm just kind of approximating just what the shape looks like. The values themselves don't make a whole lot of difference. So I don't need to be hitting like the table and plotting specific points for these. As long as I see what's going on in general, that's going to be good enough. So I look at this one, and I say, okay, so as I'm heading off to the left forever here on x to negative infinity, which direction are we going? Positive infinity. And as I keep going forever to the left, I'm going down, so I'm going to negative infinity. So a quick sketch of the graph gives us enough information to just kind of follow along. The only other thing I'm going to have you do is figuring out on some of these what domain and range is going to be. Now again, we remember domain and range from before. What's domain and range ask us about? Right. Where are different x values and where are different y values going to be for these? So I have to get a sketch of these. And I need to be a little bit more accurate on this than I have on the others. So I have some options here. We're still going to mainly look for just a sketch idea. So I've got x squared plus 3, and I'll graph that. Now, since I'm a little more specific this time, I do need to know where that bottom point is. So I look at domain, and I'm like, okay, that's my left to right here. If you wanted to, you could, in this case, go to the table to try and see where that lowest value is. Ooh, symmetrical. I remember this. So 0, 3 would be my lowest point. And to be perfectly honest, from there, if I want to be real accurate, I can with some other points. But since I'm just doing a sketch to try and figure out my left, right, my up, down, once I get it sketched, here come the questions. So domain is my x, which is from left to right. Nice, okay? This arrow, even though it may not look like it here, is going to slowly keep stretching out and out and out, and so it is going to is here as well. So it goes from negative infinity to infinity. Because if I were to bring my table back up, I notice the numbers for y keep getting bigger and bigger and bigger and bigger. There's no sign of them getting smaller. So that's my left to right. It's going to keep stretching forever. My x values keep doing that. For my range, it's bottom to top. Where does my graph start as far as my y values go? 3. And then they just go up forever, 3 to infinity. So don't make these like crazily difficult, because 3 would be included as one of my values as I'm starting to head up. If it weren't included, then we'd have to use the parentheses. But with these, the bracket's going to be necessary. And as I do some of the other ones, all I'm basically doing is I want to get myself a sketch. Now this is going to be kind of a funky looking graph. It's definitely not a parabola. So if you're like, well, how am I supposed to get an accurate depiction of that? I'd go back to the table. Whoa, those are huge numbers. I don't think those are going to fit. Let's get back to the numbers that fit here. Well, kind of this funky, lopsided looking W shape. So what I'm basically going to do is I'm only going to plot the points that actually will fit on my graph. So it looks like starting at -2, 9, negative 1, 0, 0, 1, 1, 6. And those look like the only ones that are going to fit. So I'm just going to come back here for a minute. I want to get an idea of what this is going to look like. Okay, again, not looking for complete perfection because you're going to start noticing a pattern develop with these. What's my domain going to be? Negative infinity to infinity. That's going to happen an awful lot. Range, what's the lowest value that I plotted? 0 to infinity. Okay, so you don't have to be an expert at graphing to make this work. All you've got to do is go ahead and get it typed in. Try to get a little less glare here. So I have an idea of what it's going to look like. Okay, kind of a squiggle here. Again, go back, get a general idea. Don't have a lot of points that are going to even plot this time. 0, negative 5, 1, negative 4, and 2, 1. Otherwise, they're like way off the charts both directions here. So I'm like, all right, this kind of goes like that. Okay, again, not perfect, but again, we're just doing sketches. We're trying to get our domain and range. Yeah, my domain, this is going to keep stretching out, and so is this. You're like, dang, it's like domain always going to be, maybe. And then range this time, it keeps going forever down and forever up. Infinity to infinity. So you just have to get that general sketch to be able to figure out how this is going to work. So your task is to tackle the worksheet that goes. So don't even have to deal with a book today. Is to tackle the worksheet that goes along with it, just to get some practice in the different areas of these. And then tomorrow we'll go over that.